Alright, so now we're in section 4.3 where we're going to talk about how derivatives affect the shape of a graph. Something we've been talking about since when we first talked about derivatives is that a positive derivative corresponds to an increasing function and a negative derivative corresponds to a decreasing function. We've also just seen that when a derivative is zero, we might have a local minimum or a local maximum. How can we tell whether we're at a local maximum or a local minimum? Well, we have something called the first derivative test. If I'm at a local maximum, that means I must be increasing up to the maximum and then start decreasing. So if I have a critical number of f of x, and if f prime changes from positive, increasing, to negative, decreasing, at x equal to c, we have a local maximum because the function is going up, and it stops, and it comes down. Similarly, if the sign of the derivative changes from negative to positive, that is, the function is decreasing, stops, and then starts increasing, then we have a local minimum at c. However, if the derivative does not change sign, that means that there's neither a local maximum nor a local minimum. Okay, but that's the first derivative test. Okay, as an example, let's find the local maximums and minimums of f of x equal to 3x to the fourth minus 4x cubed minus 12x squared plus 5. The first thing we're going to do is to find the critical numbers so that we can apply the first derivative test. We take the derivative, get 12x cubed minus 12x squared minus 24x. When is this equal to 0? Well, I set it equal to 0. I factor. I get 12x times x plus 1 times x minus 2 equal to 0, which gives me 3 roots, 0, -1, and 2. Now this is a polynomial, so it's defined everywhere, so I don't have to worry about the derivative not existing, so these are my critical numbers. Next, I'm going to find where f prime of x is positive and negative. It's a continuous function, and I figured out where it's equal to 0. So that means that on every interval between any two consecutive critical numbers, it always has to be positive or negative. Otherwise, it would hit the x-axis someplace between one of these two zeros. We'd have an extra critical number. Okay. So the way I like to do this is I'll take a number line, and I'll plot my critical numbers on it, and then I'll say that it breaks it up into a bunch of intervals. 1, 2, 3, 4. From negative infinity to -1, from -1 to 0, from 0 to 2, and from 2 to infinity. Now in each of these intervals, the derivative is always going to be positive or negative. Also, each of the factors of the derivative is always going to be positive or negative. So all I have to do is figure out whether each of these factors is positive or negative on each interval. For example, from negative infinity to -1, 12x is negative, x plus 1 is negative, and x minus 2 is negative. I can figure that out, for example, by plugging in, say, -2 into each of these quantities. Since I have a negative times a negative times a negative, the derivative is also negative. Between -1 and 0, 12x is negative. For example, if I plugged in -1/2, I would get -6, so it's negative. X plus 1 is positive. If a number is bigger than -1, when I add 1, it's positive. But x minus 2 is negative. If a number is less than 0, when I subtract 2, it's negative. So negative times positive times negative tells me that the derivative is positive on this interval. From 0 to 2, the first factor is always positive, the second factor is positive, but the third factor is negative. So plus times minus gives me negative. The derivative is negative on the third interval. On the fourth interval, from 2 to infinity, each of the factors is always positive, so the product is positive. So the derivative is negative from negative infinity to -1 and from 0 to 2, and it's positive from -1 to 0 and from 2 to infinity. So now we can apply the first derivative test. At our first critical number, -1, we see the derivative changes from being negative to positive. That means we have a local minimum from changing from negative to positive. At our next critical number, 0, the derivative changes from positive to negative. That means a local maximum. And at x equal to 2, the derivative changes from negative to positive, which means a local minimum. And here we see what's going on. To the left of -1, the graph is decreasing. At -1, it changes from decreasing to increasing from a negative derivative to positive, so we have a minimum. Between -1 and 0, the graph is increasing, but from 0 to 2, it's decreasing. Positive derivative changes to negative at 0, where we have a maximum. And finally, the negative derivative changes to a positive 1 to the right of 2, which gives us a minimum at 2. Okay, so here's question 2. Let's find the local minimum and maximum values of f of x, which is x squared e to the x. This involves 3 steps. First, find the critical numbers of this. Take the derivative, set it equal to 0, and see if it doesn't exist anywhere. Second, determine where f prime is positive and negative. Again, it will always be positive. It will always be positive or always negative between any two consecutive critical numbers. 3, apply the first derivative test, seeing how the sign of the derivative changes as we pass from pass by critical numbers. Okay, so the next concept we're going to talk about is concavity. Now, what is concavity? It talks about how a graph curves. So we have two different forms. There's concave up and concave down. And roughly, a concave up curve looks like it is sort of curving upwards. Whereas a concave down curve looks like it's curving downwards. Okay. But another way of talking about concavity is this. A concave up curve always lies above its tangent lines, like this. And you'll see for that to happen, the slope of the tangent line has to actually increase as we move to the right, from here to here to here. So in fact, the slope of the tangents is increasing. The rate at which the derivative changes is positive. So the second derivative is positive. Since the slopes of the tangents are increasing, that means that the rate of change of the derivative is positive. The rate of change of the derivative is the second derivative, so that's positive. Similarly, concave down occurs when the curve lies below the tangent lines. For that to happen, the slopes of the tangents have to be decreasing. Well, the slope of the tangent is the derivative. If the derivative is decreasing, then its own derivative has to be negative. So that means the second derivative has to be negative. So concave up is the same as the second derivative being positive. Concave down is the same as the second derivative being negative. Okay, one more definition. An inflection point is where the concavity changes from up to down or vice versa. So that's where actually a curve doesn't really have concavity. It's almost sort of really flat at that point, but to one side it curves down, the other side it curves up. Okay, so as an example, let's find the concavity and the inflection points of f of x equal to cosine of x on the interval from 0 to 2 pi. The first thing we're going to do is find f double prime. F prime is negative sine, f double prime is negative cosine. Second, we'll find where the second derivative is equal to 0 for the same sort of reason that we find where the first derivative is equal to 0 to see where a function is increasing or decreasing. We want to see where the second derivative is positive or negative. To do that, we know this is a nice continuous function. It will always be positive or always be negative between any two consecutive critical numbers. So, when is negative cosine of x equal to 0? When cosine is equal to 0. When is cosine equal to 0? At least between 0 and 2 pi. That happens when x is pi over 2 and 3 pi over 2. So now I'm going to do the same sort of thing that we did when we were applying the first derivative test. I'm going to draw a number line with my endpoints here and my two critical numbers, and that breaks up this number line into, I'm really only concerned with these three intervals here, intervals between 0 and 2 pi. From 0 to pi over 2, the second derivative is negative. You can just plug in a value between 0 and pi over 2 and see that negative cosine is going to be negative. From pi over 2 to 3 pi over 2, the second derivative is positive. For example, if you plugged in pi, negative cosine of pi is negative negative 1, which gives you positive. Then from 3 pi over 2 to 2 pi, negative cosine of x is negative. Okay, so we found that the second derivative is negative between 0 and pi over 2, and positive between pi over 2 and 3 pi over 2, and negative between 3 pi over 2 and 2 pi. So this function will be concave up between pi over 2 and 3 pi over 2. It's concave down on the first interval from 0 to pi over 2 and from 3 pi over 2 to 2 pi. It has two inflection points where the second derivative changes from negative to positive or positive to negative, namely at pi over 2 and 3 pi over 2. So this is our picture. Here is cosine. It's concave down between 0 and pi over 2 and from 3 pi over 2 to 2 pi. Concave up between pi over 2 and 3 pi over 2. And it changes its concavity from down to up at pi over 2 and from up to down at 3 pi over 2. Great. Now concavity can also tell us something about whether a function has a minimum or a maximum at a point. So consider a function which is differentiable at a point and has a maximum there. Well, it has to look something like this. It has to really curve down, or equivalently, its tangent line has to lie above the curve for there to be a maximum. That is precisely the definition of concave down. So when we have a maximum, it's concave down. When we have a minimum, the curve has to curve upward like this, so it has to be concave up. Equivalently, the tangent line has to lie below the curve, which is concave up. So, since this gives us something called the second derivative test. Suppose that f prime of c is equal to 0. Then we plug c into the second derivative. If the second derivative is negative, then the curve is concave down. Since it's concave down, we hit a maximum. So if the second derivative is 0, we hit a maximum. If the second derivative is positive, then the curve has to be curving up, it has to be concave up. We end up with a minimum. So if the second derivative is positive, we have a local minimum at c. If the second derivative is 0, however, we can't conclude anything. You can always come up with examples where we do have a minimum or a maximum, but the first and second derivatives are both 0. So if the second derivative is 0, you should jump and try to use the first derivative test. So let's apply the second derivative test to f of x equal to x to the 4 minus 4x cubed. The second derivative test says first, take the derivative of f and see where it's equal to 0. Here, x is the derivative of f is 4x cubed minus 12x squared, which has roots 0 and 3. Then we calculate the second derivative, which is 12x squared minus 24x. When I plug in 3, I get 36 for the second derivative, which is positive. That tells me I have a local minimum there. However, if I plug in 0 into the second derivative, I get 0, which is inconclusive. If I want to see whether I have a minimum or a maximum there, I have to work a little bit harder. So to really figure out what's going on at 0, we kind of have to go to the first derivative test. So at 3, we already know we have a minimum, which means that the function has to be decreasing to the left and increasing to the right. So the only interval where I don't know what's happening now is to the left of 0. Well, for x less than 0, f prime of x, which is 12x squared times x minus, it was 4x squared times x minus 3, that's going to be negative. Why? Well, 4x squared is always going to be positive, or at least 0, so great, that's positive. X minus 3, if I'm taking x less than 0, subtracting 3 from something less than 0 is negative. So positive times negative gives me negative. So the first derivative does not change sign at 0. It starts negative and it stops negative. That means that f prime doesn't change at x equal to 0. It doesn't change sign there, and there's no minimum or maximum there. Okay, so now let's use the second derivative test to find the local minimums and maximums of f of x equal to sine of x minus x over 2 on the interval from 0 to 2 pi.